Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to take a look at the results of an AC voltage source, a sinusoidally varying voltage source hooked to a capacitor. So again, the voltage source looks like some sort of Vmax sine omega t. Over on the right, just like in my previous video here, I've got a phasor diagram. This phasor represents the input voltage, right? So the length of this vector is equal to Vmax. Here's an angle theta, which would equal omega t. Also can be written 2 pi f times t. And again, you got to imagine this thing rotating round and round and round. When this is here, it means the voltage is a maximum in a certain direction. When this tip rotates to here, the instantaneous voltage is 0. Vmax in the other direction, 0, and so forth. All right, and what we're going to do now is talk about how to analyze the circuit. So what happens here, again, Kirchhoff's law. If I pick a spot and go around, and keep in mind that the voltage across a capacitor is equal to Q over C. This is coming right from the definition of capacitance. If you remember, we started studying capacitors. Capacitance was defined as charge per unit voltage. It's real easy to rearrange that for voltage. So the instantaneous voltage on the capacitor is Q over C. So when we write an equation now for the loop, we're going to have Vmax sine omega t minus Q over C equals 0. Now, you got to remember what we want out of this. What we want is the current. Now, this cannot be algebraically solved for the current, right? It takes a little bit of math here. I'm going to talk about the math, and if you've had a little bit of calculus, that's fine. If you haven't, just, follow along. Not every part of this is going to be super important, but this can be solved for the current by algebraically solving for Q, which is equal to C Vmax sine omega t. Then the next step to turn this into the current is to time differentiate it, because remember, the current is equal to dq dt. So current as a function of time is going to be the time derivative of this expression. Now this is constant, so C Vmax, this is the first thing that requires a time derivative. The time derivative of sine is cosine, so this is going to be cosine omega t times the derivative of the inside function, which is equal to this omega, the angular velocity. Or, I'm sorry, not angular velocity, angular frequency. So the current here, I as a function of t, can be written the omega c times Vmax cosine omega t. Now, at this point here, this is the only step here that requires a little bit of calculus, and if you've had some, that's fine. If you're not, just from here on, very important as well. So solving for the current, let me do this on the right. If I solve that for the current, what we get is Vmax cosine omega t, and what I'm going to do is I'm going to put this omega c in the bottom. And if I do that, it would be 1 over omega c. Remember the old saying about dividing by a fraction. Now, some very important things here, and again, the math not required to see this, the calculus not required to see this part. Remember in the previous video, when we're doing the resistor, what was in this spot was the resistor R. This quantity right there, 1 over omega c, has to have units of ohms, and it does. It is kind of, for lack of a better way to put it, it is effectively a resistance, right? That quantity has a special name. It's called reactance. And there's two types of reactance, one for capacitors, one for inductors. This is called the capacitive reactance, and it's usually denoted with an X sub C here. The X denotes the reactance. X sub C is the reactance of a capacitor. The next video is going to be about an inductor. X sub L is the reactance of an inductor. So the reactance is equal to 1 over omega C. This is effectively the resistance of this circuit to current. And you'll notice that it's frequency dependent, right? This omega, this is the angular frequency. It's related to how fast this thing's rotating around. You'll notice that the reactance goes down with large values of the frequency. Let me see if I can talk about why. Why would that be? All right. First of all, let's imagine that the frequency here is going to 0. And basically, that means this voltage is basically like a DC voltage. meaning it's not changing. So picture just for an instant a DC voltage source. That's going to charge the capacitor to this polarity, right? If this is like plus minus. And remember that when the capacitors charge, as they charge up, the current falls off. So the current would go to zero very, very, very quickly. And we wouldn't have any current. So effectively, if we have no current, that would mean that if we think in terms of reactance here, you could think of it like the resistance of the circuit very, very, very high, no current. Imagine this frequency now, imagine this changing polarity, but changing polarity very slowly. So let me get rid of these. So imagine that this has this polarity. This thing gets charged, the current goes to zero, and then a long, long, long time later, quite a ways down the road, the polarity changes to this. This would discharge, but the currents overall would be very, 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 very low. Whenever this thing's charged up, it is basically fighting the voltage and keeping the current low. When the frequency is very, very, very high, it means that the voltage is flipping polarity very, very, very fast. And particularly when you put some resistance in the circuit, the capacitor never really gets charged, so it never becomes an effective part of the circuit. The higher the frequency, the higher the current's going to be. Think about it like this. If this frequency is really high, that means this is bouncing back and forth between plus minus and plus minus really, really fast. And what that does is it keeps the capacitor going from plus minus to plus minus, switching back and forth really, really fast. And if you take a current measurement anywhere, the average currents are really, really high. So I think it's probably enough on reactance. Let me just kind of overview it and move on. So capacitors hooked to an AC voltage source have this property called reactance. This is how it's calculated, 1 over omega C. It's frequency dependent. That's a very important thing. This is effectively like to think of it as the resistance for the capacitor in an AC circuit. It isn't actually a resistance term, but it behaves like it in the circuit, at least somewhat. So you can think of this as kind of a resistance. Right? Another very important thing here. So the current is equal to some number times cosine of omega t. Now we're going to compare that to the input voltage here, sine omega t, cosine omega t. These are not quite, these are not the same thing. So what I need to do here is I need to get myself some room. I'm going to get rid of this. And we're going to kind of investigate the relationship between the sine and the cosine. All right. So graphs. Let's talk graphs for a minute. We science people, we love graphs. All right. So I'm going to sketch this right here. And what I'm going to do here is I want to sketch sine x and cosine x. This is just a real rough sketch. All right. So if we're going to plot y equals sine x, that looks something like this. Keeps going, this would be pi, 2 pi, 3 pi, etc. And now let's plot y equals cosine x. All right, cosine of 0 is 1. That starts here, and I'm just going to do a few things here first. So we'd have a 0 here. This is going to be a maximum. We're going to have a 0 here. A maximum, a 0 here, there. That's enough to sketch it, I think. Let me go this way, though. So cosine wave looks like this. Y equals cosine x. And then this one was y equals sine x. I probably should have did them in different colors, but the important thing here is how do we turn a cosine wave into a sine wave, right? And this has to do with horizontal shifts. Remember, if we take a function f of x and we look at f of, say, x plus 1, the difference between these is the f of x plus 1 would be shifted left by an amount 1. If it were f of x minus 1, this would be a graph of f of x shifted right by an amount 1, right? So what we're going to do is we're going to apply that concept here. The difference between these two graphs, you'll notice if I move this one over to here, they would be exactly the same curve. So the cosine of sine x and the sine of sine x have exactly the same shape. The only difference is a horizontal shift. So I can shift this one over to here or this one over here. What I'm going to do is I'm going to take this one and imagine shifting it over here. Now this distance on the graph would be pi over 2. So sine of x, and I want to shift left, so x plus pi over 2 is equal to cosine x. Right, this is one of the theorems of trigonometry. I like to think of this in terms of shifting. So I take this sine wave. If I shift it left by pi over 2, I would get a cosine wave. So sine of x plus pi over 2 is equal to cosine x. Now, the reason that's important is right here. This can be written, right, V max over, and I'm going to just write this x sub c here. Right, remember the capacitive reactance. And this cosine of omega t can be written sine of omega t plus pi over 2, right, by this stuff over here on the left. Now, this is really, really important. So if this is an angle theta or omega t, the current phasor here is pi over 2 ahead of that. So if I draw that current phasor, and I think I did that in red last time, I'm going to go ahead and do that in red this time. So if I draw the current phasor on this picture, the current phasor, it looks something like this. That's the current phasor for this circuit. Now you'll notice that the current leads the voltage, and there's a very simple explanation for that, like physically. Hopefully this will make sense. Picture this voltage here, and imagine it in this polarity, plus minus. That's giving us a charge on the capacitor that looks like this, with a current direction like so. But remember, this voltage form is going to hit a peak, right? Imagine when this gets to here, the voltage will be a maximum, and then the voltage on the capacitor is a maximum. Once this voltage gets over into here now, the projection is falling off, meaning that the input voltage is smaller, and it would be now smaller than the voltage on the capacitor. So what happens is the capacitor now starts to discharge because there's not enough voltage with this polarity to keep the capacitor charged to this polarity. So basically this voltage, the input voltage, drops below, or at least tries to drop below the voltage of the capacitor, and it starts discharging. But notice, to discharge, this current has to change direction. So in the phasor diagram, what happens is we say that the current phasor is leading the voltage phasor by pi over 2. And imagine when this point swings up to here, this point will be down here, current is 0. And as soon as this swings up and then goes a little further here into quadrant 2, this point is now below the axis, and the current has reversed direction. So that's enough for this video. Again, the purpose here is to understand how a capacitor behaves hooked to an AC voltage source. Some really big things. All right, really big thing number one. When you go through the math, you end up with the current equaling V max over this quantity times cosine omega t. So this quantity has to have units of resistance. Now again, if you've had some calculus and you went through the math, that's fine. If you haven't, that's fine too. This is the really important part. We'll just pick it up right here. If you're in my college physics class, this quantity, 1 over omega c, this is what's called the reactance, or in this case, capacitive reactance. And you could think of it as the resistance of the circuit, because the higher the reactance, the lower the overall current. And when your reactance is low, the higher the overall current you get in the circuit. Very important to realize that the reactance is frequency dependent, right? High frequency means low reactance, means relatively high currents. Low frequency means high reactance and relatively low currents. Let me go through that again, make sure I did that right. So the reactance, if the frequency is very high, then the reactance is very low, gives you relatively high currents, meaning that the capacitor is not having as much effect on the circuit. When your frequency is very low, then your reactance is very high. That would give you lower overall currents. All right, so that's important thing number one here, this relationship here for the capacitor. Important thing number two is noticing that the cosine curve, all right, I can write it in terms of sine like this. And the reason I'd want to write the cosine in terms of sine is so I can compare it to the input voltage. And you'll notice this plus pi over 2. Very important that that's plus. That means that the current phasor leads the voltage phasor for the capacitor. Very important. So if you're in my class, make sure that you're taking notes right now. You should have this picture. This is fairly important here. This is really, really important, that the current phasor leads the input voltage phasor by pi over 2. I think that's enough on the capacitor. I think I'll go ahead and make another one for an inductor. Everybody have a great day.